Hi everyone, this is Tishan Wang from University of Illinois at Urbana-Champaign. Today I'm going to talk about the optimal control of a soft CyberOctopus arm. Our work is inspired by several biological experiments done in the past few decades. It has been observed that the octopus arm shows stereotypical movement patterns in a variety of manipulation tasks like reaching and fetching. For example, on the right is the video recorded by our collaborators in UIUC, which shows the bend propagation during octopus arm reaching movement. The question we're interested to answer here is that even though octopus arms have infinite degrees of freedom, why do they engage in certain stereotypical movement strategies? We're particularly interested in finding the potential optimality principles behind these strategies. Here is the outline of my talk. I will begin with the introduction to the dynamic model, which is a planar coarse rod. Then I will formulate an optimal control problem with certain objective functions for the octopus arm to reach a given target. We propose and derive the necessary conditions for optimality, known as the maximum principle. Next will be the numerical solution to the optimal control problem with simulation results. And I will end my talk with our ongoing work. Okay, let's start with the coarse rod model of an elastic arm. We model a soft octopus arm as a coarse rod, where the arm is considered as a one-dimensional continuum object parameterized by the arc length S from 0 to L0, which is from the base of the arm to the tip. L0 is the total length of the arm in its rest state. Here, we restrict our study to the planar case. For each S, we have a position vector R in a fixed laboratory frame and an angle theta, which defines the moving material frame. The position R and angle theta give the state of the arm Q. The momentum is denoted as P. The coarse rod can be regarded as the Hamiltonian system, with the Hamiltonian being the total energy. That is the kinetic energy T plus potential energy V. Then the dynamics are described by the Hamilton's equations, 6 PDEs in total. The control input U represents the force and couple generated by muscles. Once we have the dynamic model, we want to find an optimal control to achieve certain tasks, like catching a shrimp. Before we go into the problem, let's generalize the state as Z to make notations more compact. An appropriate choice of function space for the state is shown as capital Z, where you take the control set curly U to be the set of all measurable maps from the interval 0 to T to the control space U, which is taken here to be an L2 space. Then we formulate the following optimal control problem where the Lagrangian L has two components. The first is the norm square of the control U, called here as the control energy. This is a natural choice since this control cost can be related to the actual physiological energy expenditure of the animal. We also penalize the potential energy of the arm since we don't want the arm to curl too much. Our goal is to control the arm to reach a target at time capital T. The target is positioned at R target. We consider a free endpoint problem as opposed to having terminal constraint so that it's easier for numerical implementation. A terminal cost is chosen to minimize the distance between the tip of the arm and the designated target. Here, the norm is in the Euclidean sense and it does not depend on the tip orientation theta. Okay, so here is our optimal control problem. We present the first order optimality conditions for this problem. First, the co-state is denoted as psi, and the control Hamiltonian function is defined in a standard way where we restrict ourselves in studying only the normal extremos. Then we make use of the maximum principle for the Hamiltonian control system in the infinite dimensional settings. Here I state the key points of the maximum principle. The co-state dynamics is a joint equation of the state dynamics. And the optimal control gives the point-wise maximization of the pre-Hamiltonian H. Both the state and co-state satisfy the Hamilton's canonical equations. Moreover, the co-state at the determinate time T satisfies the transversality condition. The detailed derivation of these equations and other technical details can be found in our paper. How do we solve the problem? We numerically find the solution in an iterative manner, which is called the forward-backward algorithm. In each iteration of this algorithm, we first simulate the forward path, the cosworth rod dynamics, using the high-fidelity 3D simulation tool called Elastica, developed by our collaborators at UIUC. Next, the co-state is initialized by transversality condition. And then we simulate the backward path, the co-state dynamics using our custom-made solver, where the co-state evolves backward in time. At the end of each iteration, we update the control in the direction of the steepest ascent of the pre-Hamiltonian with respect to control U. We repeat the iterations until the stop criteria is met. Certain spatial and temporal discretization methods are involved in all the nonlinear PDEs in both forward and backward path equations. Please refer to our paper for more details regarding the numerical solver. Now, let me show you some simulation results. The first experiment is a simple reaching task. This video illustrates the update of the control input over iterations. The control solution converges quickly within 20 iterations. Here's other two experiments. The fetching task is set to mimic the octopus movement of fetching food to the mouth. In the shooting task, on the right, we initialize the arm in a bent configuration, which is close to the real octopus that naturally curls up at rest. The obtained optimal control actually unfolds the arm to reach the target, in contrast to the observed bent propagation maneuver. I will come back to this point later in my talk. One thing draws our attention is the waves in the optimal control solution. Particularly, let's take a look at the optimal control solution for the first experiment, the reaching task. We noticed that the wave travels back and forth along the arm, and it gets more visible as time t nears the final time T. One on the left, we visualize the control wave by color coding the couple control UC. The couple control profile is shown on the right. This resembles the EMG signals of the muscle activation recorded in a variety of earlier biology experiments. Next, we varied the parameters of our problem to analyze the speed of this wave. It turned out that the wave speed is not affected by the final time, the regularization parameters, the target position, the geometry of the arm, the numerical parameters, etc. However, it does depend on the Young's modulus and the density of the arm. And the wave speed shows a linear relationship with the square root of E over rho. This experiment indicates that the waves in the optimal control solution is actually an intrinsic property of the elastic arm. We report another interesting phenomenon, which appears when we increase chi1, the regularization parameters for the potential energy cost. A visible second wave appears in the control solution, which propagates in the opposite direction of the original wave. And two waves meet exactly in the middle of the arm. We're trying to find the connections between these waves and the stereotypical movements, especially the EMG recording experiments in the context of elbow formation. As we can see, the optimal control solutions we get don't quite match the typical octopus arm movements. However, under the current optimal control framework, the forward-backward algorithm does converge quickly and leads us to the optimal control solution that achieves the given tasks. On the basis of all the work mentioned, we are now able to consider a more advanced dynamic model. For example, we already developed a control-oriented muscle model which captures the properties of longitudinal and transverse muscles to contract so that the arm can bend and elongate. Also, we'll now take the environmental effect into account, like the gravity and buoyancy and drag force from fluid. Here is a sketch to show that the drag force might be crucial for the octopus arm to form a bend, since that will minimize the drag force and save control energy. We applied some artificial control input to the octopus arm with muscle model and drag force present. We are able to replicate the bend propagation movement, which is shown on the right. Comparing the previous results on the left, the arm without drag force just simply unfolds to reach the target. And we're still on our way to try to reveal the potential optimality behind these stereotypical movements. This work is closely done with Dr. Udit Howder. I also thank my advisor, Professor Prashant Mehta, and our collaborators, Henshin Chen and Professor Mattia Gozzola. That's all for my today's talk. Thank you so much for listening. Any questions?